All right, so on to section 5.3, exponential functions. We'll add a function, or actually a class of functions, to our library of functions. So we haven't added things to the library of functions in quite some time. And we'll do that in the next section as well when we encounter logarithmic functions. But section 5.3 is exponential functions. What we'll do is evaluate such functions, graph exponential functions. We'll define the transcendental number e, and we'll solve exponential equations. A subtlety arises in this idea of exponentiation, and it's related to rational exponents versus irrational exponents. We define what it means to raise a real number a to a rational power r, that is, we define what a to the r means, in Appendix A10, when we talked about roots and rational exponents. For example, if r equals m over n in that appendix, we define a to the m over n to be the nth root, the nth root of a to the m power with certain obvious constraints. For example, we can't take square roots of negative numbers. But this is the meaning of a to a rational power, where that rational number is m over n. We require calculus to define how to deal with irrational exponents. Some details are given in my Calculus 1 notes on section 3.8, derivatives of inverse functions and logarithms. We'll follow this textbook's approach, which is simply to describe a way to estimate a to the x when a is positive and x is irrational. What we'll do is take a rational approximation, r, of that exponent, and then say a to the x is approximately a to the r. Computationally, that'll do just fine. Conceptually and theoretically, it's got some weaknesses, but we'll get by in Precalculus 1 with this approach. So what we might do if we wanted to raise a to the square root of 2 power, the square root of 2 is famously an irrational number. Well, we could just take 10 or 12 digits of the decimal approximation of the square root of 2, which would give us a rational exponent, and then use that for the exponent. Theorem 5.3.a, it appears we've already done this before. We have not, because now we're dealing not with rational exponents, but with real exponents. So let s and t, which will act as exponents, and a and b, which will act as bases, be real numbers where a and b are both positive. What we're never defining is what it means to raise a negative number to an irrational exponent. And the interactions we're getting between exponents are the following. If we take a to the s times a to the t, we get a to the s plus t. A to the s itself to the t power is a to the s times t. AB to the s power is a to the s times b to the s. 1 to the s is 1. A to the negative s is 1 over a to the s, or 1 over a to the s equivalently, and a to the 0 is 1. What's new is the fact that we're using real numbers for the exponents s and t. Yes, we've said all this stuff before. Before we said it in that appendix, though, when we had rational exponents. Here we're saying those rules hold not only for rational exponents, as we saw before, but also for any real number, including irrational exponents, as given here. A little observation again, the a and the b are greater than 0. They're both positive. One thing we haven't defined, nor will we ever, is 0 to the 0 power. 0 to the 0 power will remain undefined. We've got a is positive here, so a is not allowed to be 0. In addition, a is not allowed to be 0. We don't have any division by 0 in this expression here. So the properties of exponents you're familiar with, they hold whenever exponential functions are defined. An exponential function formally is a function of the form f of x equals constant times a to the x power, where a is a positive real number not equal to 1, and c is a real number not equal to 0. If c equals 0, we just have the 0 function. So that's why that constraint. A is positive because we haven't defined what it means to exponentiate an irrational number with a negative base. We have to have that base a to be positive. And we're taking a not to be 1. If a is 1, we simply get 1 to the x power, and this reduces to the constant function f of x equals c. So not for theoretical reasons are we eliminating a base of 1. For pragmatic reasons, we're doing that. The domain of this function is the set of all real numbers. Any real number can be an exponent on a positive base. The base a is called the growth factor of a. And c is what we would get by plugging in x equals 0. F of 0 would be c a to the 0. And we just stated above, a to the 0 is 1, provided a is positive. And so this c parameter is called the initial value for that reason. When x equals 0, the function produces the value c. That's why it's called the initial value. Kind of think of starting at x equals 0. With f of x equals c a to the x, f of x plus 1 would be c a to the x plus 1. Composition of functions. Then if we were to look at f of x plus 1 divided by f of x, we'd have c a to the x plus 1. After all, that's the numerator. And that would be divided by f of x, c a to the x. But we've got our properties of exponents. A to the x plus 1 divided by a to the x, we would subtract exponents there and simply get a to the 1, or a itself. And of course, the c's cancel. So what we're seeing is the exponential growth of this function, and it's related to this parameter a. The exponential function f of x equals c a to the x, where a is not 1. We said exponential function, so it's understood a is positive. C is not 0. If x is any real number, then from this formula, we get the behavior f of x plus 1 divided by f of x equals a. Cross multiplying, we get f of x plus 1 equals a times f of x. Okay, all that arithmetic and algebraic manipulation is fine, but here's what this really means. So if we increase the x value by 1, this function grows by a factor a. I guess grows if a is greater than 1, shrinks by a factor of a if a is between 0 and 1. But we're getting this multiplicative type behavior. If we were to go to x plus 2, we'd pick up another factor of a, and we have a squared times f of x. If we went to x plus 7, we'd have a to the 7th times f of x. So these functions, these exponential functions, grow like crazy if a is greater than 0. I'm sorry, if a is greater than 1. If a is between 0 and 1, then they decrease like crazy. And we'll illustrate that with some graphs. In fact, here's our first addition to the library of functions since, I don't know, maybe chapter 2 or chapter 3. If we plot points, we find that the exponential function f of x equals 2 to the x, f of x equals 2 to the x, has the graph given here. I don't like plotting points to graph functions, but it's all we've got since we've been introduced to this new function. And we're putting a little faith in Sullivan that this graph is accurate. In calculus, you'll be able to confirm that this is an accurate graph, but 2 to the x. So we're going to go through and plug in x values as exponents and get out powers of 2 as outputs. Plug in 0, 2 to the 0, that's 1. So we get the 0.01. X equals 1, 2 to the 1. Plug in 1, get out 2. Plug in 2, get out 2 squared, 4. Plug in 3, get out 2 cubed. So this point would be somewhere up here, 3, 8. Plug in -1, get out 2 to the -1. That's 1 over 2. So we get the point -1, 1/2. -2, 2 to the -2 would be 1 over 2 squared. That's 1/4. Plug in -2, get out 1/4. Plug in -3, get out 1 over 2 cubed. That's 1/8. So what's happening is, as we move to the right, we're getting bigger and bigger values, and quite rapidly, this grows exponentially. As we move to the left, we're getting smaller and smaller positive numbers. A is positive. Every power of A will be positive. A is 2 in this case. Every unit we move to the right by 1, the value doubles, as we observed in this previous theorem here. So if we go from 1 to 2, the value increases from 2 to 4. If we go from here to here, the value of the function will double from 4 to 8. We go from 3 to 4, the value will double again from 8 to 16. So you see this geometric growth, it's sometimes called as well. We see this growth by factors of 2 every time we increase the input by 1. If we move to the left, we see that moving to the left, we're backing up by 1. So instead of multiplying by 2, we divide by 2. Value here is 1/2. Move back 1 unit, it's half of that, 1/4. Move back 1 unit, it's half of that, 1/8. Move back another unit, it'll be 1/16, and then 1/32, and then 1/64, and so forth. So this is what the exponential function f of x equals 2 to the x power looks like. This is what, in a broad sense, this is what an exponential function a to the x looks like whenever a is positive. The numerical values will change, the steepness will change, but the general shape will remain rather the same. And that's the next topic. If we vary the base a in an exponential function, f of x equals a to the x, we find that for the larger values of a, the graph takes on bigger values for x greater than 0 and lesser values when x is less than 0. For example, let's compare 3 to the x and 6 to the x. The 6 to the x values are going to be bigger than the 3 to the x values when x is greater than 0, and they'll be less than when x is less than 0. Is the claim, and here's the graph. So in black, we have the graph of 3 to the x. Plug in 0, get out 1. You know, when you plug 0 in to one of these functions, a to the x power, a to the 0 is always 1. They're all going to pass through the point 0, 1. Plug 0 in, get 1 out. On the right-hand side, the powers of 6 will be greater than the powers of 3. At 1, at 1, the 3 to the x function produces a value of 3. At 1, the 6 to the x function produces a value of 6. So bigger, simply because the base is bigger. Let's move over here to 2. 3 to the x would produce 3 squared, would produce 9. 6 to the x would produce 6 squared, which is 36. 36 compared to 9. This one grows a lot faster than this one. Yeah, it's because the base is bigger. Moving to the left, we get reciprocals of the values on the right. For example, at -1, 3 to the -1 is 1/3. There's the graph at that point. 6 to the -1 is 1/6, if it shows. And on this scale, that 1/6, there it is right there, is pretty close to 0. That's the reason they didn't move any further to the left. If I plug in -2, here we'll get 1/9. Well, you could probably see that on the graph. Here, -2 would give us 1/36, and that's going to be, on this scale, extremely hard to distinguish from 0. Of course, it's different from 0. These functions never take on the value 0. In fact, they put a dotted line in here to be discussed here shortly, as if these have some sort of horizontal asymptotes. They do. So this is what happens when you make the base bigger. Say base a equals 3 compared to a base a equals 6 exponential function. Bigger bases yield functions that grow faster and get bigger on the right. On the left, they get smaller as we move to the left. And it's because of a reciprocal behavior between the left and right. When a is greater than 0, So this is the case we've only addressed so far. We'll consider a between 0 and 1 here shortly. The exponential function has the following property. Domain, all real numbers. Any real number can be an exponent of a when a is positive. And here we've got the additional constraint that a is greater than 0. The range is a set of all positive real numbers. Range would be the y values. Yeah, if I take 3 and raise it to a big power, I get big numbers out. This is just heads upwards. It's unbounded above. That should be quite plausible. 3 to the x never equals 0, though. 3 to any power will always be a positive number. But when you put these negative numbers far to the left in big negative numbers, it's going to be a tiny, tiny, tiny little number. If I were to take x equal to 10, negative 10, then we'd have y equals 3 to the negative 10. That's 1 over 3 to the 10th power. 3 to the 10th power, I don't know why I choose that, is 3 to the 10th power is a huge number. And so its reciprocal is a tiny number. Just as these things get huge and positive on the right, they get tiny and positive on the left. They never take on the value 0, but any value greater than 0, eventually moving to the left, these curves will take on those values. So the range is all y values strictly greater than 0. The range is all positive real numbers. In interval notation, the interval 0 to infinity. No x-intercepts. Y-intercept is 1. Yeah, it never reaches the x-axis. As I said, these always pass through the point 0, 1. Plug 0 in, get 1 out, a to the 0. We're considering exponential functions of the form a to the x. Always get this point out. All exponential functions of the form a to the x always pass through the point 0, 1. And that's the y-intercept. The x-axis, that is the line y equals 0, is a horizontal asymptote as x approaches negative infinity. Some symbols from calculus that we've dealt with earlier. Yeah, this, as you move further and further to the left, it gets closer and closer to the x-axis, and it never gets there. We've been through an elaborate story about what asymptotes are and what they are not, but this function does behave like that. The further to the left you move, the closer you get to 0, and you never get there in that sense. That's not what an asymptote is, but satisfying that property yields an asymptote. And I think this is the first time we've seen it have an asymptote on the left and not have an asymptote on the right. Possibly we dealt with piecewise functions. They could behave like that. Rational functions do not. If they have an asymptote on one side, they got the same asymptote on the other side. This does not. This has an asymptote on the left and no asymptote on the right. These get super steep. They don't have a vertical asymptote, though. Remember, the domain is all real numbers. A to the x as a function is increasing, and it's 1 to 1. Again, this is the case a greater than 0. Increasing function in 1 to 1, yeah, certainly. Gets steep, fast, continues. This function's always increasing when read from left to right. It's tempting to read from right to left and say, well, I follow this direction. It gets closer to the x-axis, the line y equals 0. But it's still, that makes it an increasing function. I don't read in this direction in an increasing, decreasing conversation. But it's always going uphill, really shallowly on the left and really steeply on the right. So it's a strictly increasing function. It's a 1-to-1 function. That is a horizontal line. We'll intersect it in exactly one point if that horizontal line is above the x-axis. Of course, if that horizontal line is the x-axis or below the x-axis, it doesn't intersect it at all. But that satisfies the conditions of being a 1-to-1 function. It satisfies a horizontal line test. Graph always contains the points -1, 1 over a, 0, 1, and 1a. Remember, we're dealing with a function a to the x. So plug in -1, we get a to the -1, which is 1 over a. Plug in 0, we get a to the 0, which is always 1, at least for these values of a. And we plug in 1, we get out a to the 1, or simply a itself. So that gives us kind of 3 key points, as the book has called them in the past, when we deal with graphs. The graph is smooth and continuous with no corners or gaps. I'm kind of taking the Sullivan's word on that, the textbook author's word on that. Yeah, I guess the graphs look like this and they are smooth. How do you know they don't do something crazy in between these 2 points, like wiggling up and down? Well, we didn't test all those points, so I guess we don't. It doesn't behave like that. It does behave as graphed, but we don't quite have the knowledge to establish that. So we are taking the author's word really for this last one about continuity and smoothness. Okay, that was an analysis of the case for an exponential function when a is greater than 1. What about when a is less than 1 and greater than 0? We're going to analyze that by considering y equals 2 to the x and y equals 1/2 to the x. So if we replace x with negative x in the graph of y equals 2 to the x, and you know what the graph of this looks like, we added it to the library on the previous page. So we're talking about this function from figure 18. F of x equals 2 to the x. Suppose we replace x with negative x. As we saw in the section on transformations, that's equivalent to a reflection about the y-axis. Reflection about the y-axis of the original curve, y equals 2 to the x, if you replace x with negative x, one of the reflection transformations. So we'll get that geometric behavior. By replacing x with negative x, we'll produce the new function 2 to the negative x. That's the same as 2 to the negative 1 to the x, properties of exponents we mentioned earlier. 2 to the negative 1 is 1/2, and that gives us 1/2 to the x. So the graph of 1/2 to the x is what we get by taking the graph of 2 to the x that we just looked at and reflecting it about the y-axis. We'll look at a picture in a second, but what we're going to do is take this curve and reflect it about the y-axis. Replace x with negative x. That means what happens over here on the right gets reflected around to something over here on the left, and what's happening over here on the left gets reflected over to behavior on the right. So what we would get would be a super steeply decreasing function that would come through and pass through this point, and then have an asymptote on the right of 0. The graph is as given here. If you take that previous curve, reflect it with respect to the y-axis, it'll produce this curve. We can also take powers of 1/2 and see that these values are correct in terms of the points plotted. In fact, if we compared y equals a to the x to the function f of x equals 1/x, we get the same kind of behavior. That is, if you wanted to consider the graph of 1/3 to the x power, we'd take 3 to the x, replace the x with a negative x, and that'd result in 1/3 to the x and a mirror image of this black curve with respect to the y-axis. Reflect about the y-axis, then we'd have a curve that has this type of shape here. So reflect the black curve about the y-axis, and that'll give you the graph of y equals 1/3 to the x power. In general, a to the x reflected about the y-axis will produce a graph of 1/a to the x. So here's some properties of exponential functions. F of x equals a to the x, where a is less than 1. And remember, we had to keep a positive for various reasons. We can't raise 0 to the 0 power. We can't raise negative numbers to irrational powers. That's not even defined. And the problem underlying this, of course, is square roots of negatives in some sense. So the only other options for the base of an exponential function are a is between 0 and 1, strictly between, A equals 1 doesn't give us an interesting function. It gives us a constant function. And it's not considered an exponential function. It's not one-to-one. So take A between 0 and 1. What do you get in terms of domains and ranges? Same thing we had in the case A is greater than 1. For example, here's 1/2 to the x power. Domain, all real numbers. This is defined for any input. Output, again, is strictly greater than 0. So the range is all positive real numbers, the open interval from 0 to infinity. X-intercepts, no x-intercepts, just like before. On the right, it's asymptotically approaching 0. It is getting closer and closer, and it never gets there. So that does imply the existence of a horizontal asymptote on the right to be dealt with here shortly. But the curve never touches or crosses the x-axis, so no x-intercepts. Y-intercept, we still get the point 0,1. We had the point 0,1 on 2 to the x, so on 1/2 to the x, we get that same point. Remember, we reflected about the y-axis. Any points on the y-axis stay on the y-axis, like the y-intercept. The x-axis, y equals 0. Y equals 0, of course, is the formula for the x-axis. They indicate in pink or so here. This is a horizontal asymptote as x approaches positive infinity. As x moves to the right-hand side, the curve has the horizontal asymptote of y equals 0. Left-hand side, no asymptote, right? The left-hand side is growing like crazy. As well, it's heading off upwards like crazy is a better way of saying it. It's always a decreasing function. Notice when read from left to right. So I try to choose my words somewhat carefully. That's part 4. It's a decreasing function. It's always going downhill when read from left to right. It's a one-to-one function. Satisfies the horizontal line test. Any horizontal line will intersect it in at most one point. Exactly one point if that horizontal line is above the x-axis. If that horizontal line is the x-axis or below it, doesn't intersect it at all. As long as a horizontal line doesn't intersect it in 2 points or more, we're good. So horizontal lines intersect in at most one point. That means we got ourselves a one-to-one function. The graph of this function includes the point -1, 1 over a, 0, 1, and 1 comma a. Again, same thing as we had before for the same reasons as before. So this time, remember, a itself is between 0 and 1. So a is less than 1. 1 over a is greater than 1, by the way. And taking Sullivan's word for it again, the graph is smooth and continuous with no corners or gaps. Continuous, no corners or anything in it. I could draw it without picking up my pencil. It simply decreases and is a continuous function. A topic to be dealt with in great detail in Calculus 1. Exponential functions will be dealt with in great detail in either Calculus 1 or Calculus 2. Let's do a couple of examples from this section. All right, number 38 says, match one of those equations with that given graph. Okay, first, this doesn't look straight up like any of the exponential functions we just talked about. The exponential functions we talked about, the a to the x functions, always had the x-axis as a horizontal asymptote. Also, they were always non-negative. So that allows us to eliminate a bunch of these. In A, we've got y equals 3 to the x. Well, we saw 3 to the x was non-negative. Well, it looks something like this. So it's not A. This was always non-negative. Actually, part B, y equals 3 to the 2x. We take 3 to the 2x and rewrite it as 3 squared to the x or 9 to the x. Okay, that's an exponential function of the form a to the x. And it also would be non-negative. This one's negative, so it can't be that. Part C, this is a power of 23. a equals 23. Okay, well, then that would have this same shape. It'd be super steep. But anyhow, it'd have the same shape as the a to the x functions we dealt with earlier, where a is greater than 1. And it'd be non-negative. That can't be it. Part D, 23 to the 2x. Do that same little trick and write that as 23 squared to the x. 23 squared, I guess, is 529. Okay, that one grows like crazy, but non-negative. And this one's negative. So it can't be any of A, B, C, or D. Such functions also, if we took a to the x, have to be increasing, and this one's decreasing. So there's another way to eliminate it. Increasingness, the negativeness of this function, that's a problem. All right, let's go to another slide and look at E, F, G, and H. E takes the 3 to the x function and subtracts 1. Subtracting 1 is a vertical shift down by 1 unit of the graph of 3 to the x. 3 to the x is an increasing function. You shift it downward by 1 unit, it's still an increasing function. This is a decreasing function. Can't be E. Choice F is a horizontal shift to the right by 1 unit of y equals 3 to the x. We've taken x and replaced it with x minus 1, resulting in a horizontal shift to the right by 1 unit. Maybe review the transformation stuff. We did move to the right because this parameter, we usually call it h, this parameter h is 1. We replaced x with x minus h. Anyhow, all we've done is taken the exponential function 3 to the x and moved it horizontally 1 unit to the right. Even if you messed up and thought it was 1 unit to the left, still that'd be an increasing function. And this is not an increasing function. So it can't be F. That leaves G and H, both of which are somewhat more complicated. G is 3 to some power. You take 3 to a power, you'll get something positive out. So G is a function which is always positive, and this function isn't, it's negative. So I've got a problem matching A through G, either from the decreasingness of this function or the negativeness of this function. Well, if it's none of those, A through G, it must be H. So process of elimination, but let's chat about that briefly. Hey, y equals 1 minus 3 to the x. We could start with 3 to the x, introduce a negative, a reflection about the x-axis, and consider negative 3x. And secondly, do a vertical shift up by 1 unit, that is, add the 1 in. And indeed, that would produce this. So we'd start with a 3 to the x function, would look something like this. Flip it over, would look something like this. Would have a horizontal asymptote to the left of the x-axis, and then move it up 1 unit. The moving it up 1 unit, that's how that horizontal asymptote got at y equals 1. And we could have probably eliminated a bunch of these in terms of the behaviors of the asymptote as well. Use transformations to graph this. Okay, that's kind of similar to what we had. We'll start with a library of functions deal, 2 to the x, and then we'll do the manipulations. Determine domains, range, and horizontal asymptote. All right, so we'll start with a graph of y equals 2 to the x. First, replace y equals f of x by y equals negative f of x. That is, we'll consider negative 2 to the x. That gives us the negative sign there for step 1. Such a manipulation is a reflection about the x-axis. When you change f of x to negative f of x, the result on the graph is a reflection about the x-axis of the original function. And we get the negatives there. Next, let's replace x with x plus 3. And then we'll have the negative in the x plus 3. We'll just be missing the 1 out front. X plus 3, I wish to interpret as x minus negative 3. The substitution we made was something of the form x minus h. As we mentioned before, here h itself is negative. So that indicates a shift to the left in the negative direction by 3 units because we have h is -3. Again, might be a good idea to review the transformation section from chapter 2 or chapter 3. So we'll start with 2 to the x. We'll do the reflection about the x-axis to get -2 to the x. We'll do this substitution to get -2 to the x plus 3. That is a shift to the left by 3 units. And finally, we need the 1 in there. We'll add the 1 in. That corresponds to a vertical shift up by 1 unit. We added 1. So the steps are: start with y equals 2 to the x. First, reflect about the x-axis. Second, shift left by 3 units. Third, shift up by 1 unit. And that will result in this function. So x-axis reflection, left 3 units, up 1 unit. And that gives us the following. Okay, here's the y equals 2 to the x in blue. Reflect about the x-axis, flip it over. Produces something like this in green. Y equals -2 to the x. Next, we replaced x with x plus 3. That was a shift to the left by 3 units. So we'll take the green curve, move it 3 units to the left. Move it 3 units to the left, that will produce the red curve. Didn't label key points, but key point would be 0, 1 right here. Flip it over, we got the point 0, -1. Shift it to the left 3 units. We should have 1, 2, 3. We should have -3, comma, -1. So here's that key point. If you want to keep up with the key points, it's a good idea. And then finally, we'll shift the red curve up 1 unit. By the way, this goes from being at -1 to being at 0. It went up 1 unit. And here's a key point right there that corresponds to this original key point. But flip it over, reflect about the x-axis, shift it to the left 3 units, and then shift it up 1 unit. That last shifting implied that we get this horizontal asymptote of, should read y equals 1. Y equals 1, little typo, I will get that corrected in the online notes. Instead of y equals 0, we get y equals 1 as the horizontal asymptote. They wanted based on the graph, so now we're looking at this particular function, the domain. That domain's all real numbers. These exponential functions, the domains are all real numbers. The ranges are a little tricky to find, especially if they've been transformed. Range, what do we get out of the purple function? Everything less than 1. Nothing never equals 1 or anything greater than 1. Anything less than 1 comes out. So the range is -infinity to 1, open interval there. We don't get the value 1 out. It has an asymptote there. And it has y equals 1 as the horizontal asymptote, as it should be labeled. So there's transformations applied to that new library of function, f of x equals a to the x. So new function, and we're just doing old things to it, transformations, for example, and moving the graph around. The next definition isn't well motivated at this stage. It's tradition to cover this topic in pre-calculus. The textbook states, many problems that occur in nature require the use of an exponential function whose base is a certain irrational number symbolized by the letter e. As they say on page 276 of the 10th edition of this book. The number e is the base of the natural exponential function and the natural logarithm function. Now, it's totally unclear what's natural about these at this stage, especially when I give you an approximation of this value e. It's an irrational number, so that's probably not good. It's a transcendental number, in fact, whatever that is. But when you view some of the calculus properties of exponential functions, that will give a naturalness to the exponential function. It's a calculus property that makes it natural. So for your information, click on the hyperlink there. That'll take you to some notes that deal with derivatives. And this differentiation idea is what reflects the naturalness of a natural exponential function. This number e can be defined by taking a limit as n approaches infinity of the quantity 1 plus 1 over n to the n. A limit, well, we haven't defined that, but we've used the limit notation when talking about asymptotes. Idea is you plug big numbers for n in, and that gives you an approximate value of e. Were we to plug a big number in, you'd find that e is to a bunch of decimal places, but nothing special, 2.7182818282459, blah, 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 blah. Continues without bound, it's an irrational number. So why you would want this for the base of your exponential, nothing natural about it at this stage. But anyhow, if you don't mind putting your answers in terms of e's, we can still treat this like any other exponential function. It'll satisfy the additive properties of exponents when we multiply exponentials together with a common base. So this is an important number. We'll encounter this number again and again in the remainder of chapter 5. So I don't know, get over it. We're stuck with this number. It really is a natural thing, but it's just something we can't explain in Precalculus 1, what's natural about it. But we can manipulate it symbolically like we would any other exponential function. Equations that involve terms of the form a to the x, maybe that a parameter could be this number e even, where a is greater than 1 and not greater than 0 and not equal to 1. Usual constraints on a when we considered the exponential function a to the x. Equations involving these are called exponential equations. Such equations can sometimes be solved by the fact that a to the u equals a to the v implies u equals v. That's because these are one-to-one functions. Since they're one-to-one functions, if a to this equals a to that, then this equals that. The exponents must be equal. One-to-oneness of exponential functions gives us that property. If we don't have powers of the base on both sides of the equation, then we're stuck. We'll get a little unstuck in the next section. We'll have some more sophisticated manipulations to do involving something called logarithms. But for now, in this section, we'll have to have a to some power equals a to some other power to solve anything now. So let's do 5 examples. Back to the supplements. Solve the equation 3 to the negative x equals 81. Well, as just suggested, the only way we're going to do this in this section is if the right-hand side is 3 to some power. And 81, well, 81 is 9 squared. Hey, and 9 is 3 squared. Multiply exponents, and we get 81 is 3 to the 4th power. So we can rewrite this equation as 3 to the negative x equals 3 to the 4th power. Well, if 3 to the negative x equals 3 to the positive 4, then by the one-to-oneness, we must have this exponent, negative x, equals this exponent, 4. Multiply both sides by negative 1, we get x equals 4, and the solution set is simply negative 4. And if it wasn't of that form, at this stage, we couldn't deal with it. But we'll have more equipment later. Let's do another one. Let's do one with a base e. Maybe I go back and, there was nothing special about the 3. We had powers of 3 everywhere. Nothing special about that. Just as long as we had the powers of the same base, we were good to go on this manipulation. In this one, we've got powers of the same base. The base is e. The base is largely irrelevant in these manipulations. Okay, so e to the 4th to the x times e to the x squared equals e to the 12th. This is the power of e. And we can use the properties of exponents, theorem 5.3.a, to write this as a single power of e. So let's take e to the fourth to the x, e to the x squared. Under these conditions, you multiply exponents to get e to the 4x. Under these conditions, common base, add exponents to get e to the 4x plus x squared. So the original equation becomes e to the 4x plus x squared equals e to the 12th. Just like on the previous example, well, the only way these could be equal is if the exponents are equal. That is, if 4x plus x squared equals 12. As long as we get the same base, we're good to go. They give you a different base on the right-hand side, nothing we can do at this stage. So these are set up for us to solve with what we currently know. Let's take this little equation and manipulate it. Let's write it as a x squared plus 4x. Swap the order there, bring the 12 to the other side. It's a negative 12. We get x squared plus 4x minus 12 equals 0. Worst come to worst, we can solve that with a quadratic equation, but it factors. I look for things that multiply to give negative 12 and add to give 4, x plus 6, x minus 2, minus 6, plus 6x minus 2x will give us the plus 4x. The product here is negative 12 as needed. So this equals 0 when x is negative 6 or when x is 2. So the solution set to this equation is the set consisting of negative 6 and 2. The role E played, E didn't play any particular role. I could replace these, all three of these E's with 3, and we get exactly the same thing. There was nothing special about the E or the 3 for that matter in the previous one. Merely the fact that you can write both sides of the equation as powers of the same base is what allows us to deal with these at this stage. All based on the one-to-oneness of the exponential functions. If 2 to the x equals 3, then what does 4 to the negative 2x equal? Okay. They didn't ask us what x equals, which is a little weird. Good thing. We don't have the ability to solve for x in this equation. But they want to know what 4 to the negative 2x is. And they've given us the information of what 2 to the x is. Well, 2 and 4 are related in rather an obvious way. So let's try to take advantage of that. 2 to the x equals 3. 2 to the x squared then would be 3 squared. 2 to the x squared is 2 to the 2x. That'd equal 9. 2 to the 2x is the same as 2 squared to the x. 2 squared is 4. Ooh, 4 to the x equals 9. So with appropriate manipulations, the inspiration is I'm trying to get a square on that 2. So I'll have a power of 4. We've produced this. 4 to the x equals 9. Well, the question wasn't what's 4 to the x, but what is 4 to the negative 2x. So we need a factor of negative 2 in that exponent. So let's take 4 to the negative 2x, write it as 4 to the x to the negative 2, property of exponents. We just saw 4 to the x equals 9, so we'll substitute that in right here. We'll get 9 to the negative 2. Negative exponents mean take reciprocals. That's from the review material. We get 1 over 9 squared. 9 squared is 81, so we get 1 over 81. So it's a trick. Had they asked us for 5 to the negative 2x, it never would have worked out. Had they asked us 8 to the negative 2x, we could have done a similar trick because 8 is a power of 2. 5 is not a power of 2, not a nice power of 2 at least. So it's set up to work with this little trick. You know, we solve the problem without ever finding x. Yeah, that's because we don't know how to find x. We don't have a technique for finding x just yet. We will in the future when we deal more with logarithms, and that starts in the next section. Here's a graph. Determine the function. Okay, they say it's an exponential function of some sort. that is a function of the form f of x equals c a to the x. So we'll need that coefficient in there. So this is what they mean more specifically in their instructions. I can elaborate on that, I suppose. But we're looking for a function of the form f of x equals c a to the x. I see powers of e as the outputs, as the y values. So I expect this to involve a base e. But we'll see. Here's the function, the form of the function we're looking for. The graph passes through the point 0, -1, right there, 0, -1. So if we plug 0 in for x, we should get out -1. Plug 0 in for x, we get ca to the 0. Here it is down here. Ca to the 0, a to the 0 is 1. So we simply get c out, and we need that to equal -1. So c equals -1, and we're halfway there. We just need a. Let's use another point to find a. So we know c is -1 based on this point. Let's use this point, 1's a nice number, to see if we can find a. The graph passes through the point 1, -e. So we must have f of 1 equals -e, but we can compute f of 1 as f of 1 would be ca to the 1, ca to the 1, a to the 1 is a itself. C, we just saw c was -1, substitute in there. Simplify, that gives us -a. And remember, this f of 1 must equal -e because we have the point 1, -e on the graph. So -a equals -e, and a equals e itself. And we found everything we needed. We needed a and c. A is e, c is -1. And f of x is -e to the x. That makes sense. How would you produce the graph of this from the graph of e to the x? By taking the e to the x function and multiplying by -1. E to the x function lives up here in the first and second quadrant. If you replace it with its negative, replace f of x with -a, f of x, that's equivalent to a reflection about the x-axis. You take that exponential function and reflect it about the x-axis, indeed, it'll produce this thing here. Not that I need that to determine the answer, but it's got that geometric interpretation lying underneath it, since we simply got a negative times the exponential function. And finally, real world example. By now, you know that means ugly numbers. I'll need a calculator to evaluate these. Any standard calculator has an exponential function, base E, on it. The atmospheric pressure P on a balloon or airplane decreases with increasing height. The pressure measured in millimeters of mercury is related to the height h in kilometers above sea level by the function P of h equals 760 e to the negative 0.145 h. All right, that's an exponential function. There's c, here's a. Numerate the exponent is a little bit of decoration in it because it's a transformation of an exponential function, strictly speaking. But here's their function. Find the atmospheric pressure at a height of 2 kilometers. What is it at a height of 10 kilometers? So we'll plug in 2 and 10. H equals 2 kilometers. Plug that in here. P of 2, 760 e to the blah, 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 2. Right, 2 goes there. Multiply the exponent, get negative 0.290, and totally stuck with this. I mean, this is the precise value, but we need a calculator to go through and convert it into pressure. Pressure was measured in millimeters of mercury, they say. So from a scientific calculator with a base E key, we will find this is 568 and some odd millimeters. What about 10 kilometers? Well, let's see if we can't make some physical sense out of this. It says atmospheric pressure decreases with height. We've gone from a height of 2 kilometers to a height of 10 kilometers in part B. So the pressure should go down. As the height goes up, the pressure goes down. Plug in 10, that is, we find P of 10, put 10 in for H in that exponent, run the numbers, and we get 178. And indeed, the pressures drop quite significantly from 2 kilometers to 10 kilometers. So there's an illustration simply of a manipulation of a function. Can't get these numerical approximations out without a calculator, without a scientific calculator. But that covers all the nuances we're interested in for exponential functions up front. In the next section, we'll do logarithmic functions. Logarithms are inverse functions of exponentials. And these are the topics of chapter 5. We started with compositions, then we did inverse functions, now exponential functions, next inverses of exponential functions, and that's logarithmic functions. So I will see you in the next section. Have a nice day.